Here, I'll give you a point, right, for showing up. I was hoping to have the exams done today. I'm probably 2 hours away, unfortunately, from grading them. Right? Pardon? You can all, yeah, we can all grade them together. Actually, they're not too hard to grade. It's one nice thing about giving out a sample exam beforehand is that the exams you get really aren't that hard to grade because most people have seen the exams before, right? Before the exam, so they shouldn't be too far off. What I'm going to do here, this question actually came up, and I was going to do this lecture here at the end. First, let me make an announcement that we will have class Monday next week, right? But then Wednesday and Friday we will not have class. I will be in Clearwater Beach, Florida on Wednesday at a required meeting since I got this very nice grant. It's required of me. And I am flying back in on Friday, but I don't think the plane's due to land like 12:05. I don't think I'm going to make it here by 1 o'clock on Friday. Okay, so we will have class only Monday next week, and you have plenty to do. We can do that. And the final assignment is due. I have to make it due on the final exam day, right? At the final exam time. That's when since they know it's Monday is the final exam day. Is it? Okay, then does it say Monday on the due date? Because I checked on the CS site and it said Friday. Okay, I'll check this out. Okay, make sure that I don't take extra credit off for me or something. What I always warn, though, on the final project is don't get so far behind that you spend all finals week working on this project and you destroy all your other final exams, please. Okay? There's always professors that come to me saying, your students in your class said they worked so hard on your problem they did lousy on my final. I don't like to hear that. Okay, so work on it before the final exam week to get it in. So today I'm going to show you a couple things. The problem here that people have is what they want to do is they want to fly a camera along a certain path. Okay, and this happens in animation all the time. You want to fly a camera along a certain path, and you want it to be somewhat smooth. Okay, and how do you specify this path? It's Chaikin's curves, paths, things like this don't quite work out as well. And so there's a nice set of curves called Catmull-Rom. Okay, these are called Catmull-Rom curves. And Ed Catmull is the CEO of Pixar, and he did this when he was a graduate student. And Raphael Rom has disappeared. I don't know where he is anymore. He was an artist at one point that was working through some computer graphic stuff. But these curves are actually they're actually pretty simple, and they're what we call interpolating curves. And interpolating curves, what they do is if you specify a set of points, and the curves go through these sets of points. Okay, they're guaranteed to go through the sets of points here. And what you want them to do is you want them to be smooth, right? Especially if you're running a camera around. Running cameras around is something that's really sensitive. Okay, to movement of the camera. And you want these curves to be smooth. That you don't want to have a curve that looks like this. Okay. For mathematicians, sometimes this is okay. It's a continuous curve, right? It doesn't have any jumps in it, but the derivative has a jump in it. Okay. The derivative to this curve, slope of this curve kind of comes in here and then has this jump, right? That it does. And so the derivative has a continuity jump in it. And these are typically called C0 curves, meaning they're continuous, right? The zeroth derivative, or the function itself, is continuous. There are also C1 curves. C1 curves are the original curve's continuous and the derivative is continuous. Okay? And C2 curves are even better. although they're much, much harder to get. C2 curves are where the first derivative is continuous, the function is continuous, the first derivative is continuous, and the second derivative is continuous. So kind of the curvature is continuous, is kind of the second derivative. And so these things are all very important. And when you started running these curves around, what you want things is you want these to be fairly well behaved, and you don't want bad things to happen. There's something called the Lagrangian interpolation spline. And this is what they like to teach in a numerical analysis class, the Lagrangian interpolation spline. And it basically is a curve that goes through these points like this somehow. Okay, it's a curve that goes through these points, but it can act very badly. It's actually got a nice little mathematical formulation, which is why the mathematicians love it. Right? But it really acts very badly, and it's very susceptible to what we would call noise. Here's something kind of a linear curve, and if I take a point here and I just barely move it off the linear curve a bit, okay, you would expect to get a curve through here that looks really nearly smooth. And what the Lagrangian interpolation spline does is this, okay, which is really bad if you're trying to run a camera running around. It actually takes a divergent path out, okay. And you would like, for example, for your curves to kind of stay, if you put a box around these points that you went through, you kind of like the curve to stay inside the box, right, if possible, right, or close to inside the box. And so, this one doesn't do it. And the Catmull-Rom spline does. And they did it kind of off something called the Ferguson curve. Now, if you look at this lecture, you're going to realize there's a whole bunch of people that were working on curves back in probably the 70s and late 70s, working on different types of curves and trying to get these things to come out. A Ferguson curve says the following. Suppose you have a cubic. Suppose you want a cubic type curve. It always looks like ax, or let me call it t cubed plus bt squared plus ct plus d, right? And if you look at a cubic curve like this, you realize that you have to have 4 pieces of data in order to specify a cubic curve. You have to have 4 pieces of data. And so what they did was they said, okay, suppose I have these 2 points here, like this, and I want to draw a curve in between these 2 points, right, somehow. Well, I need 4 pieces of data in order to be able to do this. And I have 2. I have the 2 points, right? And I need 2 additional pieces of information to do it. Now, people have done all kinds of stuff here for these 2 additional pieces of information. But what Ferguson said was, okay, one of my pieces of information is going to be the derivative there, and the other piece of information is going to be the derivative here. Okay? And so if I specify the 2 points and I specify the 2 tangent lines, I can draw a nice little cubic through here. And it's not too hard to figure out how to do it. That if you let this be, let's call our curve P of something, but let's call our curve P of t here. And P of 0 is going to be this point, say P0. And P of 1 is going to be this point, say P1. Okay? Then what I'm specified here, what I have, the 4 pieces of information are P of 0, P of 1. I have these 2 points. Then I have P prime at 0, the derivative at 0, and I have P prime at 1. Okay? Like this. Everybody still with me? That's pretty easy. If you look up here, P of 0, if you let this be equal to P of t, right? Let's just play with this equation for a bit. P of 0 has to be A, right? No. No? Thank you. Okay? You are paying attention, right? Right? P of 1 has to be A plus B plus C plus D. P prime at 0 better be, I hope, C. right? So I take the derivative here, right? P prime of t, I better get 3a t squared plus 2bt plus c, right? And p prime of 1 is equal to 3a plus 2b plus c. Is that okay? Okay. And now you have these nice 4 simultaneous equations, right? You can solve them, right? You can solve them, right? D is equal to P of 0. C is equal to P prime of 0, right? Plug those in here, play some games, and out you come with a nice little set of equations, okay? That you can solve. And so, you know, you can kind of figure out what this curve is. Okay? And this curve, let's see, should I do this to you guys? Okay. Here, if I write P of t as a t cubed plus b t squared plus ct plus d, and you get that is 1 t squared t cubed, come on, times, I think, oops, a, b, c, and d, like that. Do it backwards. Okay. And I can arrange this in a form that kind of looks like this. What am I trying? Where am I going here without solving that equation? This is equal to. Will you let me do this? Times P of 0, P of 1, P prime of 0, and P prime of 1. Okay? Now, let's see. The first thing has to be D, right? So can you see this first row has to be 1, 0, 0, 0? Is that okay? And this one has to be, the C here is P prime of 0, so this has to be 0, 0, 1, 0. Okay, and as I solve these things, I can write this 4 by 4 matrix down, which is kind of cool. 4 by 4 matrices are what we do, okay, in this class. We have graphics engines that do 4 by 4 matrices. So if I put a different T in here, right, I can generate this out. This is one of the things that graphics people continually get used to doing, is we turn equations like this into matrix equations because we have this great big huge parallel matrix engine to deal with. Okay, and there's a 4 by 4 matrix here. I can't remember what the rest of it is, right? But we can convince you that it's just simultaneous equations, right? I can solve for it and figure out what this equation is here. Okay, so by sticking these points in here and placing in different t's, right, I can play with this equation and get this curve out. And this is called Ferguson's curve. It wasn't used too much until this came along, and Ferguson did this in the late 60s probably. I mean, it's really pretty trivial once you start playing with it. But what Catmull and Clark did was the following. They said, suppose I have this curve here, okay? And go ahead.
How close does the Ferguson curve come to the Bezier curve?
Well, the Ferguson curve can be turned into a Bezier curve really easily. All you have to do is over here on this little picture here, right? All you have to do is know that with the Bezier curve, there's a point out here on the tangent, and a point out here on the tangent, which are your Bezier points. Okay, you can calculate those points really easy over here. So it's really identical. Well, it's a cubic, right? And a Bezier is a cubic, so you can go between these very easily. Okay, to go between them. In fact, there's a 4x4 matrix that goes between them very nicely. Okay, there's a 4x4 matrix that does. So you can do Bezier here, right? But it's actually pretty straightforward to do. Okay. Now if I go over here and here do these points here, P1, P0, P1, P2, P3, P4, and P5. Okay. If I do these points, what I'd like to do is draw a curve between these. And in order to do that, what I'm going to do is I'm going to draw a curve in each little segment. Okay? And I'm going to get them to match up so they're actually quite nice. And what Catmull-Rom said to do was probably about as simple a thing as you can think to do. What I've got to do here at P1 in order to draw this segment, right, I need to know the derivative here at P1. Okay? And they said, well, make the derivative, make the slope at P1 the same as the slope of the line between P2 and P0. Okay? Make the slope of the line here that. Okay? Make the slope of the line at P2 equal to the same as the slope of the line between P3 and P1. See what I'm getting at? And then you get this guy, get this slope here. And once you have this, you have 4 pieces of information, and you can draw that use segment of curve, use your imagination. And that's tangent there at the top. Same thing here. P3, I can take P4 minus P2 and get the slope at P3, right? And I can get a cubic curve that does that. Okay, cubic's nice because I can have an inflection point. P4, I can take P5 minus P3 and get the slope here. And off I go. Okay. And I can draw this curve. No matter how many points I have, I can draw this curve. My only problem is what to do at the endpoints. Okay? Because I don't have an extra point out there, right, to use. And well, they said, okay, we'll just put you can do this several ways. Okay? What they typically did is they said, we'll put an extra point out there. Okay? What we can do is just take this distance here and, take this thing here and put another point out here, sorry, same distance away, collinear, okay? And make this is called a phantom point or a ghost point on the curve. And then you can use this point to get a derivative here, right? Subtract these two, get a derivative here, and then you can make this last line come in. Same thing over here, put an extra point out here, right? Same distance away, so this slope here is that, and then you got something that looks like that, etc. So you have to play a game at the ends, okay? You have to play a little game at the ends in order to do it. One of the other things they did was at the end, you need 4 pieces of information in order to be able to do this curve, okay? You can say, okay, here's a point, there's a point, here's a slope. We need 1 more piece of information on this end to do it. And what they said was, oh, assume the second derivative is 0 here. Okay, so it kind of flattens out. Assume the second derivative is 0. Okay? And that'll give you the 4th piece of information. So you have to calculate it a little bit differently on the ends. Okay? And what happens here is that you get a real nice little system that you can calculate out, okay, that actually is pretty nice, okay? And, and it produces a very, very nice interpolating curve very quickly, okay? Now you can convert it to, as you said, you can convert it to a Bezier if you want, but each piece here is a separate Bezier piece. The nice thing about the curve is it is what we call a C1 curve, because we kind of ensured that the tangent coming into this point is the same as the tangent going out. Okay? So there's no jump in the tangent like there was before. The tangent going in to one point is the same as the tangent coming out to the other. And this works out. Okay? It works out pretty well. And you can do this in 3D. right? The curve in 3D works also. And it's what most people use this Catmull-Rom spline mostly to set up cameras in three-dimensional space and move them around. Okay? Now, with a camera, there's lots more than the path of the camera to worry about. Okay, if you're going to do animation, things have to move kind of realistically. So you also have to move, if you have these three vectors and the camera point, all this Catmull-Rom spline does is fix the camera point. Okay? You also have to map these three vectors on how you want to move them. Okay? Which can be done with another one of these curves. It has to be done carefully, but can be done with another one. Can be done with three additional curves, one for the endpoint of each one of these things. But the thing in animation that you do, and by the way, there's a course called TCS 120 next quarter. 130, thank you. There's a course called TCS 130 next quarter, which is effectively taught over in Technocultural Studies, which is art. It's being taught. We have this interesting computer science professor who has half of his appointment in computer science and half in art, which is an interesting appointment. But he teaches a course over there that teaches Maya, which you guys now are really set up to do. Right? Some people take that course actually before this one, in fact. And in there, what you want to do is you want to actually move you want to do animation and things like this. Well, the other thing with animation that makes it difficult is that when you move a camera around, cameras don't start and stop instantly. Okay, they don't go from 0 velocity to 1 velocity in an instant. They have to go over a particular number of frames. They accelerate, right, and they slow down. Same thing when they turn. They don't turn. The rate of turn of a camera doesn't jump from 0 to some instant rate instantaneously. Right, as you move these cameras around, they have to move very, very smoothly. And so you always have something, as you're moving along these paths, you always have a secondary function that if you want your camera to move at a certain velocity, that ramps you up to this velocity and then ramps you back down at the end. Okay, so you have to plan your camera path so that you speed up, right, run for a while, and then you slow down. Or if you're turning the camera, you speed up, right, to the real turn rate, and then you slow down. So you actually have to think of these things very carefully when you're placing cameras running around. And it's one of the things people do in videos, people have trouble with in videos, is that to move the camera, it has to be moved over a set of steps. It has to accelerate up to speed, it has to move, and it has to decelerate. If it's going to rotate, right, it's rotational velocity. You have to work up to that rotational velocity and then work down. And you kind of have to integrate all these things together. It's not too hard to do once you do the first one. People tend to use sine functions or something like that to do this. I tend to use Bezier curves, right? Bezier curves that look like this, right? If here's the origin, here's one control point, and then the control point up here, like this. And what happens is the initial velocity, right, tangent there is 0, and it ramps up, comes in here like this. Okay, I tend to use Bezier functions that look like this in order to accelerate and decelerate cameras running around, and paths running around, and people running around, and things like this. Okay, as long as the slope isn't too fast, right, or really too slow, your eye doesn't notice it. Right, things tend to go fairly smoothly. But the TCS 130, right, is a course where you actually discuss now how do you animate things, right, and move things around. And the kinematics of objects, moving objects around, is really complex, much more complex than some of the things that we actually end up doing. So this was the Catmull-Rom spline. People, you can use, I mean, there are interesting things to use this. I could extend this lecture by another 20 minutes by actually figuring out these matrices here and all, okay? But I'm going to wave my hands at it. That this one, p prime of 0, right? This one ends up as the, let's see, I'll have to write it down. suppose I have these 3 points, P0, P1, P2, and P3 here, something like this. Okay, then the derivative here, P prime, right, I'm going to get then P of 0 is equal to P1, P of 1 is equal to P2, P prime at 0 is equal to P3 minus P1, P2 minus P1, thank you, and P prime of 1 is equal to, thank you, is equal to P3 minus P1. Okay? And you can take all this information and the A, B, C's, and D's over here, solve some high school simultaneous equations, and what you get is you get a function that looks like P of t equals 1t, t squared, t cubed, and here's a 4 by 4 matrix, right? And here are the points P0, P1, P2, and P3. A little different than that one over there, okay? But since these derivatives can be written in terms of these guys, okay, you can actually write these things down, and you can come up with a 4 by 4 matrix in here that works for any point t. Then all you have to do is put in the points t's here, the p's here, you're done, okay? And it's actually a fairly simple 4 by 4 matrix too. But you know, there's 10 minutes of high school algebra here we could do in order to figure this out if we wanted. But you know, so that all I have to do then is piece these. Oops, and this gives me this piece right there. Okay, it gives me that piece right there. So all I have to do is put these together. So this is called the Catmull-Rom spline. I wanted to show it to you before we get done in the course, because some people can use it if they want to move cameras around. And it's very, very valuable to move cameras around. And it's very, very simple, and it's out there in OpenGL. Okay, it is out there in OpenGL. Okay, I am going to finish 20 minutes early, and have a nice 4-day holiday. This is where you catch up on all your classes, right? And we'll see you on Monday.